Dear students, welcome to my YouTube channel, आओ chemistry सीखें. Let's enjoy chemistry. Today I am here before you with my fifth lecture on electrochemistry, and the topic for today is determination of transport number by Hittorf'S method. This lecture will be helpful for BSc students. So आओ chemistry सीखें. Let's enjoy chemistry. Before starting, let's have a quick recap of what we had studied earlier. As we have discussed, whenever electrolytic solution is taken in a container and electricity is passed through it, ions start moving towards their respective electrodes. And these ions are the charge carrier. So whatever electricity flows through the solution, ions are the carrier of that electricity. And each ion, or better, each type of ion carries a fixed fraction of total electricity passing through the solution. This fraction of total current or electricity carried by an ion of ith kind is known as its transport number. Mathematically, it is given as Ti is equal to Qi upon Q, where Qi is the electricity carried by ith type of ion and capital Q is the total electricity passed through the electrolytic solution. Transport number is also known as transference number. It is designated by symbol Ti. Transport number of ions are the fractions. We can have an idea that sum of transference or transport numbers of all the ions present in solution will be equal to unity, or transport number of cations plus transport number of anions will be equal to 1. Transport number of ions can be determined experimentally. There are generally three methods employed for the experimental determination of transport numbers. These are number 1 moving boundary method, number 2 Hittorf's method, and number 3 EMF measurement method. Out of these three, the first one I had taken in my last lecture, and today we are going to study the principles and experimentation of Hittorf's method. Dear students, before going to Hittorf's method, we have to learn one very important aspect of electrolysis. So in this slide, we are going to learn that aspect. Here is an electrolytic vessel. In this vessel, an electrolytic solution is filled and cations and anions present in the solution are marked as plus and minuses. Also, two electrodes, cathode and anodes, have been immersed in the solution. Vessel is divided into three imaginary compartments by putting imaginary partitions at A and at B. So name of these three compartments are cathodic compartment, central compartment, and anodic compartment. The solution present in and around the cathode is called as cathodic compartment. Similarly, the solution present in the vicinity of anode is called as anodic compartment, and solution present between these two compartments is known as central compartment. We have to keep it in mind that these are just imaginary compartments which help us to understand an important concept of electrolysis. And also in this picture, before electrolysis, 8 pairs of cations and anions are present in all three compartments. Here you can see cathodic compartment has 8 pairs of cation and anions. Similarly, central compartment and anodic compartment also has 8 pairs of ions.
Now, what will be the result if potential is applied across cathode and anode? You can very well tell. On applying the potential, the ions will start moving towards their respective electrodes. As we have just said, each compartment has 8 pairs of cations and anions. That means each of the compartment is electrically neutral. But when potential is applied, then ions start moving. For example, cations start moving from anodic compartment to central compartment and central compartment to cathodic compartment. Similarly, anions start moving from cathodic compartment to anodic compartment through central compartment. As a result, the concentration around cathode and anode will start decreasing. At the same time, we know that ions have different mobility. That means number of ions moving from cathodic to central, then central to anodic will not be same as number of ions moving in reverse direction. So we can say on applying the potential, the concentration around cathode and anode will definitely decrease, but the decrease in concentration will not be the same because the number of ions moving depend on their ionic mobility. So the fast moving ions will result into more decrease in the concentration than slow moving ions. So there will be decrease in concentration around cathode and anode on applying potential, and this decrease will directly depend on the ionic mobility.
These important theoretical studies about electrolysis were made by Hittorf, and whatever we are discussing here in the form of this theoretical vessel with three different chambers and movement of ions from one compartment to other compartment is known as Hittorf theoretical device. One important generalization comes out from all this discussion with the help of Hittorf's theoretical device, and this is electrolysis results into decrease in concentration around anode and cathode, and mathematically fall of concentration or decrease in concentration around anode is directly proportional to mobility of cation, because when EMF or potential is applied, cations move from anodic compartment to cathodic compartment. So fall in concentration around anode will depend on ionic mobilities of cations. Or in other words, fall of concentration around anode is equal to a constant multiplied by ionic mobility of cations. Similarly, we can apply it to the fall of concentration around cathode, which will be proportional to ionic mobility of anions, or fall of concentration around cathode will be equal to a constant multiplied by ionic mobility of anions. If we take these two equations, this one, and divide these two, we will get a better equation like this: fall of concentration around anode divided by fall of concentration around cathode during electrolysis will be equal to mobility of cations divided by mobility of anions. We are going to make use of this last equation in our Hittorf's method of determination of transport number. Coming to Hittorf's method. Hittorf's method makes use of fall of concentration around a given electrode to determine the transport number of a specific type of ion. From Hittorf theoretical device, so far we have got this equation, that is fall of concentration around anode divided by fall of concentration around cathode during electrolysis will be proportional to mobility of cations and mobility of anions. If you remember, by definition, transport number of cation is equal to mobility of cations divided by mobility of cations and mobility of anions. Since mobility of particular type of ion is proportional to fall of concentration around the respective electrode, so we can write values of U plus and U minus in terms of fall of concentration around the electrode. So transport number can be redefined as transport number of cation is equal to fall of concentration around anode. That means instead of U plus, that is ionic mobility, we have written fall of concentration around anode. And instead of U minus, we have written fall of concentration around cathode. So this is the new definition of transport number, which is written in terms of fall of concentration around the electrodes. If we look at the denominator says that fall of concentration around anode plus fall of concentration around cathode. If you look at electrolysis process seriously, then this fall of concentration around anode plus cathode is equal to total fall in the concentration of electrolytic cell. So in Hittorf's method, we can write total fall in the concentration of cell in terms of gram equivalents. If concentration is measured in terms of gram equivalent, then total fall in concentration of the cell can be rewritten as total number of gram equivalents lost from the cell. That means whenever electrolysis takes place, ions move towards their respective electrodes, and after reaching the electrodes, they get discharged. After getting discharged, either they bubble out in the form of gases or they get deposited on the respective electrode. As a result, there is loss in the concentration, and this total loss or total fall in the concentration of cell is equal to total loss in gram equivalents in the cell. So transport number can be rewritten in terms of gram equivalent as T plus is equal to number of gram equivalent lost from anodic compartment divided by total loss of gram equivalents from the cell. So far we have got this expression for transport number of a cation. Again, focus on the denominator. It says total number of gram equivalent lost from the cell. Electrolytic cell is filled with solution of cations and anions. When electrolysis takes place, these ions get deposited or evolve at the electrodes. So whatever gram equivalents lost from the cell, that will be equal to the number of gram equivalents deposited at each electrode. This is what Faraday's laws of electrolysis say. So total number of gram equivalents lost from the cell will be equal to number of gram equivalents deposited at cathode or at anode. So the denominator of this expression can be rewritten in terms of number of gram equivalents deposited at each electrode. This is the final equation of transport number of cation. It reads as transport number of cation is equal to number of gram equivalents lost from anodic compartment divided by number of gram equivalent deposited at each electrode. Suppose we want to write it for transport number of anion, then here will be the minor modification because anions move from cathodic compartment to anode. So there will be loss of gram equivalents at cathodic compartment. So T minus can be written as number of gram equivalents lost from cathodic compartment divided by number of gram equivalents deposited at each electrode. Generally, in Hittorf's method of determination of transport number, the electrolytic solution is connected with a copper or silver coulometer, and according to Faraday's second law, the number of gram equivalents deposited at each electrode will be equal to number of gram equivalents of copper deposited in copper coulometer or number of gram equivalents of silver deposited at silver coulometer. So denominator of this expression can be rewritten in terms of number of gram equivalents of copper deposited in coulometer, or T plus is equal to number of gram equivalents lost from anodic compartment divided by number of gram equivalents of copper deposited in coulometer. Experimental part of Hittorf's method. The electrolytic tube used for the determination of transport number by Hittorf's method is shown here. It is one H-shaped tube and it has got two limbs. One is cathode and another one is anode. These vertical tubes are about 1.5 to 2 centimeters in width and 20 to 25 centimeters approximately in length. Now what happens? The apparatus is filled with the experimental solution whose concentration is known, and the electrodes are connected in series with a copper or silver coulometer or voltmeter, and a current of 0.01 to 0.02 amperes is then passed for 2 to 3 hours. And in Hittorf's method, transport number can be calculated from the concentration change in one electrode compartment only. That means we calculate change in the concentration at cathode or at anode. Accordingly, from there we can determine transport number of anion or transport number of cation. So this is the brief about the experimental of Hittorf's method. We will learn the experimental part better with the help of one numerical. It has been taken from the book Principles of Physical Chemistry by Puri, Sharma and Pathania. The numerical reads as: a DC normal solution of silver nitrate was electrolyzed between platinum electrodes. After passing a small current for 2 hours, a fall of concentration of 0.0005124 gram equivalent occurred in the anodic solution. The mass of copper deposited in a copper coulometer placed in series was found to be 0.03879 gram. Calculate the transport number of silver and nitrate ions in silver nitrate. Given equivalent mass of copper is 31.8. We have been given fall of concentration around anode and mass of copper deposited in copper coulometer. Now, the formula used in Hittorf method is given here. To calculate the transport number of cation, in this case silver ions, we need number of gram equivalent lost from anodic compartment, which is given here. This is the loss from the anodic compartment and it is given in terms of gram equivalent. So we know this particular quantity. Next thing we need is number of gram equivalents of copper deposited in coulometer. If you look carefully, we have been given mass of copper deposited in copper coulometer. This is the mass given in gram, whereas we need number of gram equivalents of copper. So the first thing we have to do is to convert this mass of copper into gram equivalents of copper. How to do it? It is simple. Divide this mass in gram by equivalent mass of copper. So gram equivalents of copper in copper coulometer is equal to mass of copper divided by equivalent mass of copper, that is 31.8. This is the gram equivalents of copper deposited in coulometer. Now from this formula we have got number of gram equivalent lost from anodic compartment as well as number of gram equivalent of copper deposited in copper coulometer. So simply we have to substitute the values in this formula. This is the number of gram equivalents lost in anodic compartment, substitute it here, and this is the number of gram equivalents of copper deposited in copper coulometer. Substitute it in denominator and divide. We get transport number of cation. Once we know the transport number of any one ion, the transport number of counter ion can be calculated by using this formula. Here comes the transport number of anion. Here you have to learn one more thing. After 2 or 3 hours of electrolysis, what we do, we take out the solution from any one of the compartments, either anode or cathodic compartment, and find out its remaining concentration by a suitable method and compare this concentration with the original concentration. Then we come to know that how many gram equivalents have lost from that compartment. So this is all about determination of transport number using Hittorf's method. Hope you got the idea. Thank you very much.